Alrighty. Good morning, everybody. Welcome back to Calc 1. Plan for today is, as promised, I have a quiz for you on Standard 19. And then we will finish off our discussion of Standard 20, talking more about the net change theorem. As far as office hours go, I'll have my usual office hours today. I'm not going to hold office hours tomorrow because, like several of you, I will be doing break things. If you want to meet with me, if you're going to be around over Thanksgiving break and you'd like to meet with me, send me an email. I'll be in town. I won't be in the office every day. I might be able to set something up. And as far as homework goes, we are going to have a quiz next Monday over Standard 20. And don't forget, you also have a homework set, homework 21, that is due Monday a week from now. And no, I'm not assigning anything else. I'm not assigning any new web works over break. Any questions or comments before we get started for today? So as promised, I sent out over the weekend or I think on Friday, I sent out the table of grades, basically how many total masteries do you need to get which grade in the class. And no, that doesn't mean you can, and no, just because you need 42 total masteries doesn't mean you can do any one of them, any one of our standards more than twice. But you can get up to 2 bonus masteries depending on your overall homework score at the end of the semester. Plan is next week, Monday and Wednesday, we will have we'll do Standard 21. Maybe towards the end of class on Wednesday, if we have time, do a little bit of Q&A. We will see. And then next Friday, last day of class, will be midterm 3. The following Monday will be the final. Ain't that something?
Are you going to grade our midterms over the weekend?
Yes, I'll get your midterms graded by the next day. You probably will. But yeah, you will be able to go into you should be able to go into the final exam knowing how you did on the midterm, barring catastrophic things happening. Why was algebra always so easy for the Romans? Right?
X always equals 10.
Yeah, whenever they wanted to solve for x, they always got x equals 10. Roman numerals. All right, and with that, let's go ahead and get started on today's quiz.
side. Perfect. Thank you. Thank you.
Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Alrighty, so I'd like to go ahead and jump right back into Standard 20. Where if you recall, in Standard 20, we were talking about the net change theorem, which says that if you want to calculate the net change of a function from point A to a point B, in other words, take f of b minus f of a, then as long as your function's differentiable with everywhere between a and b, you can integrate the derivative f prime of x from a to b, and that'll be one way in order to get what the net change is going to be. And last time we looked at an example with, I don't know, you're on a boat, you're using up gasoline at such and such a rate, how much gas is lost. Where the idea behind using the net change theorem is if we have a formula for f prime of x, but not f of x, and we want to calculate the net change of our original function f of x, which has a formula we don't know and can't know just from knowing what f prime of x is, we can integrate f prime of x from a to b, preferably using the fundamental theorem of calculus and not a horribly nasty sum of infinitely many rectangles, and calculate net change that way. So we're going to be starting off today on page 2 with a classic example for all you physics fans out there, where we have a particle that is moving along a string. So picture a string in space, you get a particle moving along a string, and we know the velocity of that moving particle, that after t seconds, it's going to have a velocity of 4t minus 8 inches per second. And the question is going to be, what is the particle's displacement? Or should I say net displacement? From t equals 0 to t equals 3 seconds. So in this scenario, we're trying to find we have a particle, we know what its velocity is at any given point in time. It's given by this 4t minus 8 formula. And we want to know not what is the, what's going to be the net change in velocity from time t equals 0 to t equals 3. We wanted to know the net change in velocity, that would just be v of 3 minus v of 0. But in this case, we want to know the displacement of the particle's position. In other words, how far away is the particle's ending point from where it started. So in other words, we need to find the expression s of 3 minus s of 0. Where here we're going to let s of t equal the particle's position after t seconds. Sort of the same function we used for height when we were doing our initial value problem examples. So, Cecilia.
Yes.
If we are just given a formula for v of t, that v of t is 4t minus 8, is that enough information to get a full formula for s of t?
No, you would need like some way to find c.
Yeah, we could certainly say, well, it's going to be 2t squared minus 8t plus some constant c, but without knowing where exactly our particle started, or some initial value for s of t, we don't have any way to solve for that constant term. So what can we do instead? If we want to find s of 3 minus s of 0 here. The question for the class, not just Cecilia. Rachel?
We would want to integrate a v of t from 0 to 3.
Yeah, because if we, according to the net change theorem, s of 3 minus s of 0 is going to be equal to an integral from 0 to 3 of the derivative s prime of t of our position function, which, as we've seen, if we were to differentiate our position function, that's going to give us velocity. So we could just plug in and take the integral of from 0 to 3 of our 4t minus 8 function. So if we want to integrate this, I'd prefer to use the fundamental theorem of calculus to do it, which means we need to find some antiderivative of 4t minus 8, and then plug in our endpoints and subtract. John, what is your favorite antiderivative of 4t minus 8?
2t squared minus 8t plus 2.
Plus 2. Throw in a non-zero constant term for the heck of it.
Yeah.
Works for me. So now we need to plug in 3 and 0 and subtract what we get. If we do that, we should get, 2 times 3 squared is 9, minus 8 times 3 plus 2, minus 0 minus 0 plus 2, which is going to give us 18 minus 24 plus 2 minus 2. Okay. And we're going to get an answer of negative 6. Inches. Yeah, since our velocity is being measured in inches per second, that's probably, and time is being measured in seconds here, that's going to be a sign that our net displacement, in other words, kind of our function that tells us the change in where it's located, is going to be measured in inches. It seems that we have a negative number for our answer. What does that mean? Yeah?
It was going backwards, like away from the origin.
Yeah. For the whole interval?
No, just in total.
Just in kind of in net? Mm-hmm. Yeah. I would say that finding a net displacement of negative 6 inches just means after 3 seconds, the particle is 6 inches behind where it started. And in fact, if we were to sketch out a graph of what's going on here, from 0 to 3, our function v of t equals 4t minus 8. I think that's going to be 2, 0. What we actually just found is that if we added up this negative area down here to this positive area up here, the negative area down here had 6 more than this positive area up here. So in other words, the fact that our answer came out to a negative number meant that when we integrated v of t from 0 to 3, we had more negative area beneath the x-axis than we did positive area above the x-axis. I call this area A1, which was an area that was treated as being negative, and this one I'll call A2, which was our positive area because it was being considered to be above the x-axis. Excuse me, the t-axis. Any questions or comments so far? This one was just using the net change theorem to compute net displacement. Since we knew our rate of change of displacement, our v of t function, we could integrate that in order to find our net change in s of t from 0 to 3. Let's add a twist to this. We're going to add a twist to this problem now. Let's say instead of asking what's the particle's net displacement, in other words, just what's s of 3 minus s of 0, s of t is our displacement function. What about if we wanted to find the total distance traveled? Where if we want to find our total distance traveled from 0 to 3 seconds, what we would have to do so by total distance, I mean we're going to treat all distance traveled as being positive distance. Where if we're going forwards, we consider that positive distance traveled. If we're going backwards, we also are going to consider that to be positive distance traveled. So all distance traveled is positive regardless of direction. So what does that mean? Graphically, if you want to have all distance traveled as being considered to be positive, that's going to mean that we want to consider both the area above the x-axis and area below the x-axis as both being considered to be positive areas. In other words, we want both A1 greater than 0 and A2 greater than 0, even though A1 is below the x-axis. So for total distance traveled, when we're considering distance forward and backward to both be considered as positive, we somehow need to redo this problem in a way that's going to treat this area underneath the t-axis from 0 to 2 as being positive area instead of being negative area. Where everything is considered to be positive no matter whether it was originally positive or negative. What can we do? Does it?
Can you find the area of the small triangle?
This one?
Yeah. And then add 6 to the other one, because you know it's 6 more than that one.
Ah, we know that one's 6 more than that one, so if we know what that one is, we could take that plus 6 again. That would certainly be a way we could do it. Yeah, that would be a totally valid technique. It's not going to be what I have in mind. I'm going to pretend like we don't know the 6 number beforehand, but that would certainly be a way that we could go about approaching this one. Ellen?
Could you go through the problem and make all of the negative signs positive?
Ooh, okay. What would be a way that we could take everything that's negative and make it positive?
Absolute value.
I like it. Yeah, that's going to be the approach I'd like to take, though, Joseph. What you did certainly should work as well. Yeah, if we want to treat everything as being positive, we have a nice function that takes in negative things and makes them positive, and if they're positive, leaves it alone. That's the absolute value function. So what we can do is we can go take an integral from 0 to 3, and instead of taking the integral of just plain old 4t minus 8, our v of t function, we could take an integral of our absolute value of v of t instead, from 0 to 3. Which means we can integrate from 0 to 3 the absolute value of 4t minus 8. Oh, let's see. Who do I want to be mean to? All right, Wayne, I'll be mean to you. What's your favorite antiderivative of the absolute value of 4t minus 8?
2t squared plus 8t.
2t squared plus 8t? So you want to break it up into absolute value of 4t plus absolute value of negative 8, and then integrate?
Yeah.
Sounds reasonable, except for one problem. You can't do that with absolute values. Absolute values are sort of like square roots in that you can't just take the absolute value of each piece separately like that. It'd be nice if we could, but unfortunately it ain't so simple. So, if you want to know something really nasty, if we were to try and find an antiderivative of absolute value of 4t minus 8, because we haven't actually we don't actually have a nice formula for how we could anti-differentiate absolute value functions. I think what we would actually have to do is come up with a piecewise function. And that doesn't sound very fun. So we're going to do something slightly different. I'm going to break this up into 2 separate pieces. I'm going to do an integral from 0 to 2 of absolute value of 4t minus 8 plus an integral from 2 to 3 of absolute value of 4t minus 8. Basically saying, instead of taking the full area from t equals 0 to t equals 3 under this function, we could just take our area from 0 to 2 and add that to the area going from 2 to 3. Or if we take our area from 0 to 2 and then add on our area from 2 to 3, that should give us our total area under the curve from t equals 0 to t equals 3. And so you might be thinking to yourself, Dr. Gerstle, why did you do that? You just took a hard problem and made it harder. Now we have to do this twice. Check this out. If t is greater than 2, what do we know about 4t minus 8? It's going to come out to something positive. And if 4t minus 8 is something positive, what does that mean is going to happen when we take the absolute value of 4t minus 8? What's that? It's positive. Well, that would have happened whether 4t minus 8 came out something positive or negative. Its absolute value would always have to be positive. Let's see. Danielle, if I were to tell you to take the absolute value of something positive, like what's the absolute value of 13? What's the absolute value of 5 trillion? If 4t minus 8 is positive, what's the absolute value of 4t minus 8? Yeah, if 4t minus 8 is positive, it's going to be its own absolute value. So the second integral here, we can actually just end up writing as being plain old 4t minus 8 from 2 to 3. Because since the function we're integrating is already positive there, we don't have to worry about taking the absolute value, because absolute value of something that's always positive is just going to be that always positive thing. So since 4t minus 8 is positive from 2 to 3, that's going to tell us that we can just ignore the absolute value in that second integral at least. So now I want to look at this first integral. Let me give myself some more space. So in our first region that we're looking at, we're going to have that t is less than 2. So if t is less than 2, well, what do we know about 4t minus 8? If we were to plug in something less than 2 for t. Yeah, like 4t minus 8 is going to come out to something that's negative. Because at 2, it's 0. If t is greater than 2, then 4t minus 8 is positive. If t is less than 2, 4t minus 8 is going to be negative. What does that tell us about the absolute value of 4t minus 8? So let's see. Avery, what's the absolute value of negative 10? What's the absolute value of negative 5 trillion?
5 trillion.
If 4t minus 8 is a negative number, what's the absolute value of 4t minus 8 going to be equal to?
Whatever we get next to the positive.
This is going to be the positive version of this. So if we have a negative number and we want to get back the same thing but positive, what can we do to that number?
It's just negative 4t plus 8.
Yeah, it's going to end up being the negative of that. Take the absolute value of negative 10, we can multiply negative 10 by negative 1 to get positive 10. If we want to take the absolute value of, say, negative 5 trillion, we can multiply by negative 1 to get positive 5 trillion. If we have some expression 4t minus 8 that's always negative, and we want to find its absolute value, just take the negative of that expression, which will come out to negative 4t plus 8. So this will give us the negative of 4t minus 8, which is the same as negative 4t plus 8 when we distribute the minus sign. So now, instead of having two different integrals where we have absolute values showing up in each expression, by breaking up our integral into two separate regions, namely A1 and A2, or in our A1 region, it was negative, so to take the absolute value, we just take the negative of the whole expression. Whereas over the A2 region, between 2 and 3, our 4t minus 8 is already positive, so taking the absolute value doesn't do anything. By breaking up our area into two separate regions like this, sort of our A1 region and our A2 region, we could basically get two separate integrals that'll add up to get something positive in the end. And to do that, I think we'll need to do each of these integrals separately. Vera, what is your favorite antiderivative of negative 4t plus 8?
Negative 2t squared plus 8t plus 3.
Plus 3, okay? I love giving me these now. I joked about it when we first did this with antiderivatives, but now you all are giving me ones with non-zero constant terms just to throw an extra wrench into the works. Tyra, how about an antiderivative of 4t minus 8?
2t squared
Minus 3, okay? For the record, you don't need this plus 3 or minus 3 terms on either of these. Those are just terms that Aaron and Tyra are throwing into the works so that I have something to swoosh swoosh later. So now if we evaluate this, we're going to get, let's see, if we plug in 2, we'll get 4 times negative 2 is negative 8 plus 16 plus 3 minus 0 plus 0 plus 3. And then we have to add to that this other expression, where we'll get 9 times 2 is 18 minus 24 minus 3 minus what we get when we plug in 2, which will be 4 times 2 is 8 minus 16 minus 3. And when we evaluate all that, we'll get negative 8 plus 16 is 8, plus 3 is 11, minus 3. Negative 6 minus 3 is negative 9. Negative 8 minus 3 is negative 11, but we're subtracting it off, so we'll get a plus 11. So this will come out to 8 minus 9 is negative 1 plus 11. It's going to give us a final answer of 10 inches. Because total distance, our units for distance in this problem are given to us in inches. So it turns out that if we consider all distance traveled to be positive, both forwards and backwards, we're coming out with an answer of 10 inches were traveled. Whereas if we just looked at net displacement, meaning we're treating distance forward as positive and distance backward as negative, it came out to negative 6 inches. Basically, in other words, this number better be positive for our total distance traveled. If we're treating all distance traveled as positive, then our total distance traveled better not be negative. But in the case of net displacement, your answer may or may not be negative, depending on whether we have more negative or positive area. Versus this one is treating both A1 and A2 as positive area, and so it better come out to some positive number in the end. And so depending on what you're doing in the real world, it might make sense to look at total distance traveled rather than net displacement. Like if I were to give you a sort of problem that says, suppose you're driving with such and such a velocity, where that makes it so you end up driving backwards for a while and driving forwards for a while. How much gas is used up by the car? If your car's traveling backwards and then forwards again, is it going to be using up gas and then suddenly getting that gas back? I don't think so, which is kind of a shame because that would be a really cool car. That would be a really cool physics-breaking car. Well, you would be using up gas going backwards and forwards. So if I were giving you the rate at which gas is used up and corresponding to velocity, it might make more sense to look at total distance rather than just net distance. But on the other hand, if you just want to know how far is my starting point from the ending point, and I don't care what I did in the middle in order to get there, whether I went there in a straight line or went backwards for a while and then forward, then it might make more sense to look at net displacement. Any questions or comments about this process? I've got a question. How did I know to split up this integral at 2? Well, Dr. Gersel, it's because at 2 on the graph, it goes from negative to positive. All right, smarty pants. How did I know to do that when I made the graph? What was special about the point 2? Rachel?
If you set the linear equation equal to 0, you would get 2 here.
So in other words, if you set our v of t, the function that we're integrating, equal to 0, we know that it would switch signs at 2? Yeah. So at t equals 2, I knew that at t equals 2, v of t, which is 4t minus 8, is going to be equal to 0. So that's how I knew to swap from going negative to positive at t equals 2 there. And then if t is greater than 2, the absolute value of v of t is the same as just v of t. And if t is less than 2, then the absolute value is going to give us the negative of v of t. So from 0 to 2, I replace that absolute value of 4t minus 8 with the negative of 4t minus 8, which turned out to be negative 4t plus 8. Either way, we used the net change theorem and integrated our velocity function, but we had to throw in this absolute value and treat everything as being positive in the case that of finding total distance traveled, where everything is we want to have be positive. Whereas if we're only looking for net displacement, then we don't need to take the absolute value because we're okay with saying going backwards counts as negative. Okay, let's do another problem. And this one is going to be similar to the first problem we ever looked at this semester. Our car traveling down a road, here is a table of values. What's going on here? So, in this case, we know that we're in a car, we're traveling down the road, and we know at various points in time what our velocity is. This time we don't know how far we are from home, but like we did back in standard 1, but we know what our velocity is going to be equal to. So let's see, at time 0, our car's just starting, so we're traveling at 0 miles per hour. After 1 hour, we're going at 60 miles per hour. 2 hours, we're going at 40 miles per hour. At 3 hours, we're going at 30 miles per hour. 4 hours, we're going at 30 miles per hour. At 5 hours, oh, we forgot something. We're going back because our velocity is negative. At time t equals 6, we're going back in a hurry at negative 50 miles per hour. And after 7 hours, we're going back at a rate of 10 miles per hour. I don't know, maybe we have a cop in our car with us and they're having fun flashing their radar gun every hour on the hour. Or maybe we're pissing off a lot of cops because we're trying to travel 60 miles per hour or whatever in a 20 mile per hour zone. And so they keep flagging us over. And so the question is, from t equals 1 to t equals 7 hours, what's our net displacement? In other words, after 7 hours, if we want to be able to calculate what is our S of 7 minus S of 0, or not S of 0, S of 1. At 7 hours, how far are we from the spot where we were at t equals 1 hour? Here's the problem. If this was standard 1, where all the values in the bottom row of the table I gave you were for S of t, you would just say, oh, take S of 7, that would be negative 10. S of 1, that would be 60. Subtract the 2, and that would give us our net displacement. That would be like a standard 1 type of question. Problem is, I didn't give you S of t. I gave you V of t. Our instantaneous velocity at several different points. So we could say, let's take the integral from t equals 1 to t equals 7 of our V of t function. Zach, what's our problem with trying to integrate V of t from t equals 1 to t equals 7 here?
We don't have the equation.
Yeah, we weren't given a formula for V of t. We know V of t at a few different isolated points, at several different integer values of t, but we were not given any way to find a formula for V of t. We could try and say something like, I don't know, Dr. Gerstle, it looks like it's being positive, and it's going negative, and I don't know, it's less negative, so maybe it's a parabola or something. That's a funny voice you have there, first of all. And second of all, that's not really enough information I don't think we really have enough information to try and find a formula for V of t based off of this. So, what we kind of have here is a situation where if we were to graph out our V of t, we're given sort of these isolated points. Let's see, 60, 40, 30, 30, negative 20, negative 50, negative 10. We don't know what the car is doing in between. Maybe our V of t starts going up here to 60 at time t equals 1, then it goes back down a little bit, and it says psych again, going back down here. We don't necessarily know. We don't have enough information to say. Maybe at like time t equals 1.5 hours, a really radical song came on the radio, and we're like, yeah, this gets me pumped. I want to drive at 100 miles per hour here for 30 seconds. Pro tip, don't do that. But this is all the information we're really given and that we have to work with. And so for our t versus V of t here, we need to try and approximate the area between this curve and the t-axis without an explicit formula. Oh dear, how do we approximate areas for things? I'll give you a hint. What does the packet suggest that we do here? Does it?
L3 approximations.
Yeah, we can approximate. Yeah, we can't find the exact area under the V of t curve from 0 to 7. But something we could certainly do is to try and do a rectangle approximation for what that area would come out to. So let's see if we can find a left and right endpoint approximation for using 3 rectangles for what this area is going to come out to. So we'll start with an L3. So in L3, from t equals 0 to t equals 2, we'll have a rectangle whose height is equal to V of 0. I don't know if that's much of a rectangle, but it's what we're, sorry, not from this. Sorry, we're not going from 0 to 7, we're going from 1 to 7. So if we split up our region from 1 to 7 into 3 equally sized pieces, and can go from 1 to 3, 3 to 5, and 5 to 7. So our first rectangle, which will have height equal to v of 1, is going to look like this. Our second rectangle, which is going to have a height of v of 3, is going to look like this. And our third rectangle, which is going to have a height of v of 5, brace yourself, it's going to look like that. And so to approximate our area underneath the curve we would get for v of t from only these few isolated points, I think we can use this left endpoint approximation technique with 3 rectangles. So, Aiden, what's going to be, how can we find the area of this first rectangle here?
You would take 2 times your v of 1.
Yeah, we know that our rectangles have a width of 2, because we could just calculate that out really quickly here. Our delta x is going to be the length of the interval divided by the number of rectangles, which is 2. So we'll have 2 times v of 1. Riley, how about our next rectangle?
Sorry, I'm kind of confused on like how you got the rectangle still, but is it just 2 times 1 divided by 2?
Well, I think, I don't know, Aiden, can you explain how you got 2 times v of 1 for your first rectangle?
Yeah, so we're dividing it up into 3 equal segments. So since we have like 6 numbers that we need to get across, we divide that by 3, and each box will have a width of 2, and then the height is just the endpoint that you're taking. So in the left endpoint, we're taking v of 1 at the start.
Okay, so basically we're splitting up our region from 1 to 7 into 3 regions, each of width 2. So from 1 to 3, 3 to 5, 5 to 7. And according to Aiden, for finding the height of our rectangle from t equals 1 to t equals 3, we're just going to take our left endpoint at t equals 1 and then plug that into our velocity function, which is going to give us 60, but we'll plug that in the next line.
So for this one, it's the width is 2, and then the endpoint is 3, and that is the velocity of 3.
Yeah, so I think we're going to get 2 times v of 3 for our second rectangle. And Ryan, how about our third rectangle?
2 times the v of 5.
Yeah. Last rectangle goes from 5 to 7. So if we plug that in, we'll get 2 times v of 5. And so if we calculate that out, our v of 1 was 60 miles per hour. Our v of 3 was 30 miles per hour. And our v of 5 is negative 20, which is going to give us 120 plus 60 plus or minus 40. And it's going to come out to 180 minus 40, which I think is going to give us 140. And we're looking for net displacement, so our change in distance. Yeah, it's going to be miles because our distance measurement is miles. So L3 is going to tell us we're going to have we're going to be traveling approximately 140 miles using this left endpoint approximation with 3 rectangles. On the other hand, let's say we wanted to do the same thing, but using a right endpoint approximation, which if you go to the next page, I think I give you a spot to do that. maybe was kind of a trick question, almost. How are we going to change up our formula here if we want to take a right endpoint approximation with 3 rectangles rather than a left endpoint?
Well, you're, instead of taking v of 1, v of 3, and v of 5, you're going to start on the right side. So you can take v of 3, v of 5, and v of 7 all times 2.
Gotcha. So our widths are going to be the same, and the only difference is to find our height from 1 to 3, instead of taking v of 1, we take v of 3, etc. I like it. So if we do that, we'll get 2 times v of 3 plus 2 times v of 5 plus 2 times v of 7, which if we calculate out is going to be 2 times 30 plus 2 times negative 20 plus 2 times, what, negative 10? Which is going to come out to 60 minus 40 minus 20, which I do believe is going to come out to 0.
Wow.
Although technically you could, if you wanted to be cheeky, you could say, 0 inches or 0 light years or 0 whatever unit of measurement you want, because if it's 0, it's all the same. Yeah, so with the right endpoint approximation, you could say, no, it's going to be about 0 miles, meaning at 1 and 7, we've traveled about the same distance. Joseph, as our resident engineer in the class, I don't know why I decided you're the resident engineer. Would you, if this is a real world scenario and you wanted to know how far you traveled, I came to you and said, well, I think we've probably traveled more than 0 miles, but less than 140. Would you be satisfied with that?
Probably not, no.
Probably not, unless you really wanted some vague numbers. How can we make this more accurate?
Midpoint.
Could use midpoint. That's not something we talked about, but we could use midpoint approximation. Take S of 2, S of 4, and S of 6. Or, sorry, V of 2, V of 4, and V of 6. What else could we do that was the thing we talked about back in standard 18? Anna?
Or rectangles.
Yeah, we could always make this more accurate by using more rectangles. Make more accurate. We could use more. How many rectangles would you like to use here?
Just like use 8 of them.
Use 8
Or 7.
or 7? From 1 to 7?
6.
Or 6 of them?
Sorry, I had a hard time counting. 6.
I was saying, I think 6 would probably be better, and I don't think we could really do any more than 6.
Yeah.
Because if we did 6, we could do like V1, 2, 3, 4, 5, and 6. Or 2, 3, 4, 5, 6, and 7. Probably give us a smaller window. But if we wanted more than that, we'd have to do something like V of 1.5, V of 2, V of 2.5, or something, and those aren't all values that we're given information on for V of t. Any questions or comments? We could find L6 and R6. I don't want to right now, but I think at this point you all know what you would have to do to find those. Last question I want to ask. We have from t equals 1 to t equals 7 a net displacement that's probably between 0 and 140 miles. What if we wanted to find total distance traveled, where velocity forwards and backwards is treated as being positive? So I'm on kind of this last page of the packet again. So for earlier, for L3, we took 2 times v of 1 plus 2 times v of 3 plus 2 times v of 5. How could we change that up if we wanted to treat all velocity as being positive velocity instead of being negative velocity, potentially. Specifically, I think we could make one slight tweak here to our 2 times v of 1 plus 2 times v of 3 plus 2 times v of 5 that we had for L3. What tweak could we make if we wanted to treat all velocity as being positive velocity? Yeah?
Absolutely.
Yeah, we could take absolute value of our velocity numbers, which will basically say, even if our velocity is negative, treat it as positive anyways. So if we do that for L3, we'll get 2 times 60 plus 2 times 30 plus 2 times the absolute value of negative 20, which is going to be 20. It'll come out to 120 plus 60 plus 40, which will give us 108, which will give us something like 220 miles. And then you could do the same thing for R3. For R3, we would take 2 times the absolute value of v of 3 plus 2 times the absolute value of v of 5 plus 2 times the absolute value of v of 7, which comes out to 120. All right, that's going to do it for standard 20. Answer your question in a second. When we come back on Monday after the break, we will begin the final standard. Hope you all have a good Thanksgiving break, and I will see y'all next Monday.
We'll be going home tonight, Joe.
So there's no way to
You going home
get
tonight?